Draw two lines several millimeters apart on a piece of white paper. Now move back from the paper until you cannot distinguish two separate lines anymore. There is a limit to the acuity of our vision because light passes through the pupil, a circular opening, in order to enter the eye. Since this is an opening, there is some diffraction that occurs around its edges. And since it's a circle, it behaves a little bit differently than it does in a slit interference. The pupil of your eye is simply an opening, or aperture, that allows light to travel through it. So really it acts just like a slit does in a diffraction grating. The difference really is that the pupil is a circular opening. So the diffraction that is occurring around the edges will form a circular diffraction pattern with a bright spot in the middle and fringes all around the circumference of the opening. If you put two point sources of light close enough together, the diffraction patterns will begin to overlap. The closer the 2 points of the sources are, the more difficult it becomes to distinguish them as 2 points. If the points get close enough, there is no way to resolve them into two different images. We know that the diffraction pattern produced by light passing through a rectangular slit has a central maximum on which most of the light falls. On either side of this central peak is a minimum at some angle given by the equation of sine theta equal to the wavelength of light used divided by the width of the slit. In the case of a rectangular lens, or opening, the light is traveling through a regular opening and behaves in the same manner in any given location along the slit. However, in the case of a circular opening, the width of the opening is not uniform, but varies from its diameter d to 0. So some math has been done to account for this change in the diameter along the opening. This shows that the average width of a circular slit is the diameter divided by 1.22. So our equation for the first dark fringe of a circular lens is the sine of the angle theta equal to 1.22 times the wavelength of light used divided by the diameter. Have you been driving down the highway at night and seen what you thought was one headlight coming towards you? Probably thought, oh hey, a motorcycle. But as the light moves closer, the light sort of starts to split apart. Then once the light gets close enough to you, your eyes are able to resolve it into two separate headlights, and you realize it was not a motorcycle, but a car. When you first thought it was a single headlight, your field of view was very large compared to the distance between the 2 point sources. So them being so close together resulted in the first dark fringe of the first point overlapping the first dark fringe of the second point, and your eyes were not able to resolve them into two different points. This is the basis of Raleigh's criterion. Really, this just says that there's a minimum angular width that must separate two objects before you can distinguish them as two separate objects. And this minimum angle is 1.22 times the wavelength of the light divided by the width of the opening. This means that in order to see things that are smaller, you can either use a larger opening or light that has a smaller wavelength. The Hubble telescope is always a fun thing to talk about. So if the primary mirror on the Hubble telescope has a diameter of 2.4 meters, what is the angle between two resolvable point sources? Since we are concerned with a mirror, we can assume we are talking about visible light, which on average has a wavelength of 550 nanometers. Pretty straightforward in that we plug in those values and find that the Hubble has a resolution of 2.8 times 10 to the negative 7th radians. We can compare that to a typical Earth-bound telescope, which would be limited by the movement of the Earth's atmosphere to about half of an arcsecond. This gives us a resolution of about 2.4 times 10 to the negative 6th radians, almost 10 times less than that of the Hubble. We can see what a difference this makes by looking at an Earth-based photograph of the M82 galaxy on the left compared to the image formed by the Hubble on the right.